Hello, how are you doing?
Hi, Professor. How are you?
Good, how are you doing?
I'm doing good.
How's life going on?
All good. Just came back.
Came back from where?
College. Nothing else.
Oh, you were at school?
Yeah. No, I just came back. I had a DevOps lecture today.
Nice, who's teaching DevOps?
Greg Wesendo.
You're very lucky, you're learning a lot.
Yeah, definitely. That was
Yeah,
a very
he's
good course.
great, he's amazing. And how's grading work?
Going good so far. Completed 3 homework so far.
Good,
Yeah.
I'm happy that everything goes well for you.
Yeah, it's going good.
That's great. Okay, we wait 1 or 2 more minutes, then we start reviewing the week, what we were talking about, and different stuff. And then if you have any questions about the homework or quiz or past weeks or whatever that you need help with, we can talk about that. I noticed that in review, I waste a lot of time. So I'm trying to be faster and only talk about big stuff that you need to have in your mind. For more details, you always can go and watch the lecture video. Five or three. Okay, let's start. Okay. This week material was about testing the software and the unit testing, how we are going to use that. So during the lecture material, we covered complexity metrics, testing unit testing, different concept, pattern, and guidance that we needed, equivalence classes and boundary conditions, what we need to look at, different tools that we can use, and the challenges. Also on the separate topic, we talked about static code analysis, code coverage, and strategies for testing software. What do we mean by complexity? Design complexity defined as a function of a number of different ideas that you want to hold parallelly in order to have the bigger idea work together. In the case of software development, it's different modules, for example, or different functionality that we have that we need them work parallelly together to have the entire system working. Before doing that, we have different methods. One of them was different review techniques. We review different design models that we have. We look for the simplest and clearest design so we can work with that. Then we can look at the requirement traceability matrices. We can work with the prototype. Also, we can work with the design complexity matrix. Last week, we talked about design review, requirement traceability metrics, and prototyping that we can use. This week specifically, we talked about design complexity metrics, which covered different size of the system, coupling, and climatic complexity. What do we mean by climatic complexity? Different paths that we need to take from different functions that we have to make sure that our system works well is climatic complexity. If I have an if then else, I need to deliver two different paths for getting the final result. If I have a do until, I have one and then one shortcut. If I have a while, I have a loop, and then suddenly I have the final result. In different cases, I may have different paths for each case that I'm introducing. And for a for loop, I have a straight path and suddenly a loop that I'm creating. So why do I need to understand different control flow graph? That helps me to understand the complexity of the function that I want to look at. Imagine we are working on this simple code. If A equals to 354 and if B greater than C, A and B are equal, else A and C are equal, and give me the A, right? If I'm going to look at the flow chart of the control flow, how do I look at it? I have the start if A equal to 354, then I need to check if A greater than C, if B greater than C. If that's correct, yes, then I have A and then the result, one pass. If it's not correct, so B is not greater than C, then A equal to C and another one. On the other hand, maybe I do not have any A or C at all. So I would have another pass going on. So the execution paths that I have in this example are 3. How I can take advantage of that? I can look at different number of nodes and different number of edges to understand the complexity or predict the complexity of the function that I want to work with. What do I mean number, the edges, the linkage between each two nodes that I have? What is the node? It's a one functionality. In this example, if A equal to 354 is one node for me, then the linkage between this and the next conditions that I need to look at, if B greater than C, there is an edge, right? So in this example, how many nodes do I have? 1, 2, 3, 4, 5, 6, and 7. How many edges do I have? 1, 2, 3, 4, 5, 6, 7, and 8. So I have 7 nodes and 8 edges. Based on the graph theory, the complexity of the system can be calculated based on 2 different models. One, number of edge, it was 8, minus number of nodes, it was 7, plus 2. So 8 minus 7 plus 2 would give me 3. That means that I have 3 different passes that I may take, which is correct. Or number of predicted nodes that I have plus 1. How many predicted nodes do I have? The final result is either A equal C or B equal to A equal to B, right? So I have 2 different results. 2 plus 1 would give me 3. Till here it's easy and we can easily follow. So with doing complex cyclomatic complexity or CC, we will understand the complex, or we can predict the complexity of the functionality that we have, which helps us to traceability of the module and understandability. I would understand that this model that I'm going to create is ended up in 3 different paths, meaning when I want to test that, I need to have minimum 3 different scenarios. So the minimum number of unit tests equals the number of distinct execution paths. The minimum number of passes that I predicted is equal to different number of unit tests that I need to have. Then I have some rule of thumbs for that. If my CC is something between 1 to 10, then the code is structured with well-written and high testability. I easily can test all of the passes with low cost and effort. If it's something between 10 to 20, meaning I have, for example, 15 different passes, it's a complex code. Medium testability, I cannot successfully test all of them. On the other hand, I need to pay some money and put some effort for it. If it's something between 20 to 50, it's registered as very complex. The testability is low and it's very costly, and I need to put high effort for that. Any system with CC greater than 50, we generally think of not testable at all. It's super high, costly, and needs very high effort to be able to test some part of it. So for a general idea, we try to keep all the design that we have with something between 1 to 10 cyclomatic complexity. In some cases that we cannot, we try to not exceed more than 20. So we make sure that not only we can test it as much as possible, but also we have minimum affordable cost and effort for time. There is a report that talks about the bad fix probability. If I'm working with something between 1 to 10 CC, remember we said that that is a good code. It has high testability with lower cost and effort. In that case, the chances that I have bad fix probability is only 5%. That means 5% of the bugs may not be fixed probably. If I'm working with a system with CC between 20 to 30, I would have the problem of almost 20% of the bugs are not tested probably or are not fixed probably. More than 50 would increase the bad fix to 40%. And if I'm reaching to 100, 60% of the bugs in the system are not going to be fixed at all. Look at these two codes. The code that I have in left and the code that I have in right. Both of them have complexity measure of 5. Why both of them have 5? Because as you can see, I have 1, 2, 3, 4, and 1 return. So I have 5 results. The same thing goes here. I have a return, 1, and then 4, 1, 2, 3, 4, and the return. But which one is more complex? Although both of them has cyclomatic complexity of 5.
The right one, the second one, is more complex than the first one.
Why?
Because it has like 4 loops and like many loops inside of it. 4 loops.
Yes, exactly. The right one, because it has a lot of nested loops. Nested loops automatically create more complexity and more baby paths that we need to take. However, the general paths for both of them, or general functions, are going to be 5. Based on different case studies, we can look at the usefulness of cyclomatic complexity. For example, in Toyota, there was this problem of the cars would fail and they will directly go to, the driver couldn't control them. It resulted 89 deaths. They checked all the mechanical and electrical options possible. They couldn't understand what happened. Then it turns out that the software system that they're using, it has 67 functions that have CC greater than 50. And they have one critical function with CC equal to 146. Overall of these 68 functions was 1,300 lines of code. Practically, they couldn't test none of them very well. And when they go live, they couldn't understand which bug creates these accidents. Other matrices that we can use parallel with cyclomatic complexity is weighted method per class, which we weight each class that we are defining based on number of functions that they have. We have coupling between objects that we count the classes to which this a specific class is coupled to. Two classes are coupled with methods declared in the one class used from the same source. And then we have lines of code, total lines of code in the function. All of them can be useful in different methods when we are using for the development. We can choose which one we want to look at based on the project that we are looking at. Value of complexity metrics are very much in the development these days. There is a high correlation between the design complexity and the code complexity. So if before I can start the development, I can have an idea of the complexity of the code, I can easily make it in a, design it in a better developed way. The complexity metric should be applied all throughout all the life cycle of a project or a software that we are producing. If you remember from software architecture, we design the base architecture based on our understanding of what the system is. But then every step that we go through the development, we update some part of the architecture. So at the beginning, when I do the design complexity, I calculate the code complexity as well. But by passing time, my design became more complex, or maybe less complex because I learned better. So I need to go back and recalculate the code complexity matrices for me. And I should improve that by passing time during the development method. Another one topic that we talked about was unit testing. We said that the number of passes that we have is the minimum number of unit tests that we need to define. What do we mean by unit testing? Unit test is a code written by the developer to test a small part of the functionality of a method. So when we talk about unit testing, we do not care about the behavior of the system. We care about the integrity of a specific functionality. So unit testing covers functional requirements. Each unit test should have only one testing purpose. If we have multiple purposes, then we need to have multiple unit tests for that. Should consistently return the same result. How we can get the same result based on automation that we are trying to use. It should be isolated from environments that we are depending on. What is the example of the environment? For example, I'm testing the load that I'm receiving based on different emails. Each moment or each second, I can receive one or multiple different emails. The testing environment should be independent to number of emails that I'm receiving per point of time. Unit tests are intended to execution in an automation pipeline. Why automation pipeline? So again, I can receive the same result. It should cover the majority of program functionality. So I need to have at least one unit test per functionality that I have. And it performed prior to any integration testing. Before I start integrating different modules, I need to finish unit testing. And we need to have documentation for that, so it can serve as a developer documentation. For doing that, we are following the rule of AAA: arrange, act, and assert. Arrange is the first step that we arrange or set up the test. We know what is the unit test, what is the scenario, and what we want to test. Act is the next step when we execute to perform the test. We start writing that. And assert is the last step when we check the test that we written is passing and is working perfectly well. Why should we test any program? We want to understand valid and invalid parameters. We need to test them. So in the example of the triangle, what was the valid? The positive numbers was valid. What is invalid? The negative numbers, all the zeros. If it's not integer, it's text, for example, is invalid. We need to look at the boundaries. Boundaries is minimum, maximum input that I can have. A little bit less than minimum is not valid. A little bit more than maximum is not valid. Then equivalent classes that I can take. If I have float instead of integer, what will happen? I should test them. Remember, we cannot test all different scenarios. That's why we try to pick the best scenarios that covers most of the functionalities. Also, we need to test the parameter order invariant. In the example of the triangle, it doesn't matter if I introduce triangle with the legs of ABC or BCA. They both are the same triangle, right? So I need to test to make sure that my system understands that. For the boundary conditions we already talked about, we need to check a little bit less and a little bit more. Also for the equivalent, we cannot test all different inputs, right? So what we are doing, we create different clusters. So instead of testing all individual inputs, we put them in different groups, and based on their similarity, we test 1 or 2 of each group. If I have 10 tests in one cluster, I easily need to just test 2 of them, the one that in the start of the cluster and the one that is the end of the range in the cluster. And that would cover most of the tests that I need to do. Examples for the equivalent classes with the boundary conditions can be, if we are looking at the integers, for example, I know that I need to test a little bit less than A and a little bit more than B, right? So I can check the valid. If the X is between A and B, invalid is a little bit less than A little bit more than B. The equivalent class would be a valid value from anything. Instead of between 3 to 7, I have 4, I can check 5 as well. The invalid would be it's not an integer. For the equivalent, it can be it's too small, it's too big. So some non-integer, maybe a string that instead of number 4, I type FOUR. The same thing can go for the example of the classifying triangle. We look at the boundary conditions, all of them must be numbers, all of them must be positive. We look at the, if we have any upper limits, sum of any two should be less than the third one. That gives us the invalid triangle. If it's greater than the third one, that would be the valid triangle. So we can look at different equivalent classes that we can test under each cluster that we go. If I'm looking at 4 different triangles, I don't need to, for example, check all the any number greater than 0 for all of them. If I test one, it would go under all the 4 different type of the triangle. And the invalid for the triangles, exactly the same thing. If I look at the input, if they are invalid and they are error, if I check for ones, it covers the entire 4. So in the cluster, I only need to check 1. But there are some that I cannot go under different clusters. For example, if I have isoscale that I need to make sure that the type is isoscale, I need to do that. There is no clustering for that. And how to implement and run the test? We always try to do the automation of the testing. Why we did that? Because we can trace it back, we can repeat that, and every time that we run that, we receive a similar result. For doing that, we do the unit testing based on the automation pipeline. We can use different unit testing tools by PyUnit, JUnit, CUnit, any type of unit testing tools that you would like to use. In this class, we are using PyUnit because we are doing Python. And then we have different unit test assert methods. Remember, when we are for normal coding, we have A equal to B. That means A equal to B, right? But when I'm going for the unit testing, I need to assert that. So assert equal A and B. Assert not equal A and B. However, in the normal, I don't need to put any assert. I want to do, for example, A is B, then I should do assert is A and B. The rest of the coding is exactly like what we are doing in normal coding. So for the guideline, it would be, the test should be self-descriptive, like any other coding that we have. From the variable numbers, we can guess, we need to have the comments. We need to follow all different coding standards. We need to use meaningful names. We group related tests into a test suite. We don't include conditional logic in a test. The conditional logic and stuff goes through the development. The test is only going through the path and see if the result is what we expect to see. We only catch expectation if they are expected. If we do not expect to see something and it just happened, that's a failure in the test. 100% testing coverage, generally not practical, so we do not expect that unless the program is very small. But we try to get as much coverage as possible. Also, each test that we are running must be independent from the previous one. And when a test fails, we don't ignore that. We need to go back and make sure that we understand why it failed and how we can fix it. So how we can do that? We write a unit test whenever that we need to fix a defect. We use different parameterized tests to do that. We teach each feature, test each feature at least once. We test expected test at least once. And we try to make sure that we are not missing any test story or test unit that we need to test. Benefits of unit testing, it's reduced the defect when we have a newly developed test and newly developed code. When we're changing some existing features, it's reduced the cost of the defect as early as possible. Every time that we are changing something, right away we test that as well. It increased confidence in the code when I maintain the code or when I change the code, because I know that it passed the test. It improved design and better enable refactoring of the code. So at the end of the product, I have very well written code there. It provides metrics on quality of the building, provide documentation, and I can use unit test as the first step for regression testing, which we are going to talk about on the week 12 and 13. What are the challenges? The challenges is not all codes are so isolated. Remember the example of the email I gave you. So how can we fix that? There are different methods that we can use for making sure that our code is isolated from the environment that we can use. Also, we need to make sure that it's the consistency of the test is not dependent on the data. So the data should be consistent when I'm doing the test. If I have a dynamic data, I would not receive the same code. What do I do for that? What can I do for that? For going through that type of situation, we need to do reduce the dependencies, right? For reducing the dependencies, the solution is something we call mocking that makes my environment testing environment isolated from development environment. So if something changes, I won't have any problem in testing. What does mocking do? It replaces one or more objects or functions with the mock objects that I have. All the objects that are dynamically depend on the data or the change in the environment would switch to be static. So when I run different tests, I can have the same behavior every time. So under the mocking, we have a mock, which implements an interface of on which you can set expectations. What will the result be? And we have a stop that implements an interface but does not allow behavior to be specific. How we do that? Every time that I want to test from a dynamic system, I make a copy. Exactly what mock does is like make a copy of the entire system, put that in a in a virtual memory, and then from the virtual memory, I can access and start testing. This virtual memory is not in touch with the environment that the actual product in, so all the dynamic changes on the actual product will not be affected on the virtual memory that I have. The data that I have on the virtual memory is as updated as the last moment I get the copy. In Python 3, we have easily access to Magic Mock, which creates the mocking for us. All we need to do is just be using add patch to start activating the unit test mock in the mocking system. So in normal situation, if I want to do the testing, I have the system, for example, I'm searching for the number of repos from the commit in the Git, right? So I have the model and then I start doing the test, but I'm not sure if the number of the repos is changing while I'm doing the test, right? I need to make sure that it's isolated. So the new user do not start collaborating with the repo, right? For doing that, what I need to do is first, I need to create the mock. So instead of directly defining the test, all I need to do is I create a mock add patch. What I want to test, exactly that function, I create a copy, and then I start creating the test unit. When I mock that, whatever the data that a specific function would report would be exactly like a screenshot, would be copied in the virtual memory, updated as of the moment I ran this line of code. And the rest of the test would be applied on the data that I created in the virtual memory. When do we use that? When we need to test a program that rely on resources that is not available during the test, that they are dynamic and explicitly specify and override the behavior of the object by the changes that they have in the dynamic behavior. Any questions still here? Okay, on a little bit different but related subjects, when we are doing the unit testing, we need to do some code analysis. Remember that we do mocking because we want to make sure that the code is isolated and the dynamic changes in the environment doesn't impact on that. Therefore, the code analysis must be static. We are not doing the dynamic. The static code analysis helps us to identify anything that doesn't smell right. The advantages is it's expensive, and we can probably find security holes better than if we wait for a longer time. But there are some issues. It may provide false positive. Different tools find different security issues. So it depends on what we want to use, we may have different results. Therefore, we never use one tool only. We always try to use a combination of multiple tools to have a better coverage. This is an example code from a Python library. When they run, they have different issues, right? But how can we find the exact issue that I want to start with? We can use different tools that are out there. We can use PyFlash, we can use OWASP, we can use find bugs, or we can use PyLint. It's totally depend on you what tool you want to use. But how we are doing the coverage analysis, the goal is we measure how much of the code is being tested by the automated testing. The more we can cover, the better, and we have more confidence in the system, right? So it identified untested code framework and created a new test to cover the test. The statement coverage, with different tools, we can go through all the statements. We can go through all the branches and make sure that we have there. All the conditional tests we need to cover, all the passes and all the functions. In reality, we cannot do that, right? But in practice, we can go something around 80% coverage. For example, we can say, I did 35% statement coverage and 40% branch coverage by the time that I'm talking to you. So when we start trying we do the try and error and we go through different statement coverage, it measures the percentage of the statements that are executed. So it goes through line by line, counts the number of line of code that is already executed, and the associated test unit that we write for that. If it passed the test unit, it calculated as covered. If it didn't pass, so it's not covered. Therefore, we will have a percentage of, for example, it goes through 100 lines of code and it has 10 different unit tests. 8 of them passed, 2 of them didn't pass, so it has 80% code coverage. This is the same thing. For going through the code coverage, we can actually take advantage of the CC or cyclomatic complexity that we learned. We learned that the number of nodes and number of edges would create us the number of paths, and number of paths is the minimum number of unit tests that we need to have, right? So in two different extreme cases, the branch which merge, So the number of possible passes here would be 2 power n, right? The n is 4, so it would be 64. And this one, it would be the number of decisions plus 1. Which one has an easier way to be covered? The one in the right has the lower number of possible passes, right? The one in the left has a higher number of possible passes. So what we can do is we can look at the minimum and maximum. We can say that the CC is upper bound for the number of the test cases that are necessary, and which be 2 power n. This is the upper bound. Then the number of decision plus 1, this is the lower bound. Therefore, I need to find something between these two. The branch coverage 2 power n and the number of passes that I have, then the number of code coverage for the test cases is something between the branch coverage and number of passes. So the branch merging would be 2 power n, not merging would be n plus 1. CC should be something between 2 power n and n plus 1. That would be the number of test cases that I need to do to make sure that I have the highest level of code coverage. So the calculation that, for example, gives us the 80%. So if I go 80% of the code coverage during the unit test would be 95% plus function coverage. If I'm looking at the system, so 40 to 50% code coverage is usually achievable. I cannot do more than that. More than 80%, it requires too much effort during the system testing that we normally cannot do that. As a rule of thumb, when we do a statement coverage, we expect to go not less than 80%. Branch coverage, we normally can do 100% because we just look at the number of passes. The condition coverage, the same thing. Pass coverage, the same thing, and we know the formula how we are going to calculate that. The functional coverage, we normally can do 95% plus, but it's really hard to approach to the 100%. Between traditional waterfall and the agile, we have some trade-off. We cannot say which one is easier to do the testing and doing the more of the coverage. However, in the traditional method, we react to the quality issue. In the agile method, we react to the reducing quality issue. In the traditional, we normally do testing when it's very late. In agile, we do testing as soon as possible. So it's easier to manage and have higher code coverage in agile method. So when we look at the traditional, who is responsible for the test? In the traditional, it's the developer. In the agile, developers using automated tools. They don't do that by themselves. What they are doing in traditional, they look at the new features and bug fixes because it's very late already. In agile, they do new features, bug fixes, code branch coverage. So it's the same. The difference is in agile, they already did that 10,000 times by the time that they have a new part of the module out. In traditional, this is the first time they're saying it. When they're doing that in traditional, after the code is complete, before we go to integration. In agile, tests written before the code is even written. Remember, in the design, we need to know how we are going to test this. Last week, we talked about that. So we already have the unit test cases ready. So the traditional, we have the code, we go through that, write, debug the features, we do the unit test, we integrate the code. If it's, we do the integration. If it didn't pass, we need to go back to the unit test. If it passed, we do the system test. Not pass, again, going back to the unit test. If passed, we do the acceptance. Not doing that, not accepted, it's going back to the write debug again. In agile, we write test, we go all the tests. If they pass, great. If it's not passing, we check the unit test that is done. And when do we want to integrate? In Agile, as soon as possible, right? As soon as I have something ready, I'm ready for deliver. I share that. In traditional method, when everything is done, after all the code is complete, then now we are going there to integrate. In test-driven development, we write the test, we run the test, we write some code, we run the test, then start debugging. In Agile, we write, run, debug, all at the same, right? So who is going to write the unit regression test? The developer would write the regression test. For the advantages is developer know how they write the code and how they can test it. Disadvantages is they only focus on what they did. They may oversee other possibilities. In the pair programming, the second perspective may identify additional important testing. So if I do something, the other person may add some stuff. The disadvantages is the empirically better quality than one developer, but may not be as good as trained tester. If other developers start writing the test for me, many people thinking about the problem, so that's good. But the disadvantages is it may take longer time. So maybe it's less efficient because they follow my code line by line. If I have a separate testing team, so there are developers that only test the cases, they do not develop the system for me. The advantages, that's the advantage. The disadvantages is we need to hire additional resources. We have overhead communications and process requirement. Which one is optimal and under what condition? It depends totally on the project that we are working on. So any questions on the material we had for this week? Okay. Now let's go back to if the questions from last week's or this week homework that I can help you with. Lo, I believe you emailed me about that, right?
Yeah, I was going to wait until after if I could to speak to you one-on-one.
Okay. So let me stop recording.